Welcome back, everyone. Wave energy refers to the direct conversion of ocean wave motion into usable electricity. Portugal is an early adopter of this approach because its long Atlantic coastline offers a consistent wave climate with high energy potential. The average power per meter of wave crest along Portugal's western shores is among the strongest in Europe. Harnessing this energy requires devices that capture the oscillatory motion of waves and convert it into mechanical or hydraulic power, which is then transformed into electricity through generators. Unlike solar or wind, the physical principle here is the kinetic and potential energy of moving water. The first step in understanding wave energy systems is recognizing how waves carry energy. When wind moves across the ocean surface, friction transfers momentum into the water, creating oscillations. A wave is not a mass of water moving forward continuously, but rather water particles moving in orbital paths that transmit energy across the surface. The amount of energy carried depends on wave height, period, and length. Devices are designed to capture this motion either through floating structures, oscillating chambers, or submerged pressure devices, each tuned to the frequency of local wave conditions. One of the best-known designs is the point absorber buoy. This device consists of a floating structure that moves vertically with waves, connected to a fixed seabed foundation or a submerged reaction point. As the buoy rises and falls, a power takeoff system inside converts this relative motion into energy. The power takeoff can be hydraulic, pneumatic, or based on direct drive linear generators. For example, in a hydraulic system, the buoy's motion pumps fluid through accumulators and turbines, which then drive a generator to produce electricity. The simplicity of the buoy's vertical motion makes it versatile in different sea states. Another major design is the oscillating water column. This is essentially a chamber with an opening below the waterline, trapping a volume of air above. When waves push water into the chamber, the trapped air is compressed and forced through a turbine. As the wave retreats, the water level falls and draws air back through the turbine in the opposite direction. Special turbines, such as Wells turbines, are designed to rotate in the same direction, regardless of airflow direction, ensuring continuous power generation. Portugal tested one of the earliest full-scale oscillating water column plants on the Azores, demonstrating the viability of this approach. There are also attenuator-type devices, which are long, jointed structures that float right on the surface and align themselves with the direction of the waves. As waves travel along the length of the device, the segments flex at the joints. This flexing motion drives hydraulic pumps located in the hinges, which then pressurize fluid and run hydraulic motors that are connected to generators. The Pelamis wave energy converter, which was tested in Portuguese waters, was one of the most prominent examples. Although commercial deployment faced both financial and durability challenges, the test provided valuable lessons in joint design, maintenance, and survivability in extreme storms. The conversion of captured mechanical motion into grid electricity requires careful engineering. A power takeoff system smooths out the irregular oscillations of waves into more consistent rotational motion that's suitable for generators. This often involves using hydraulic accumulators or flywheels that can store those short bursts of energy and release them at steady rates. The generated power is then conditioned through power electronics, which adjust the voltage and frequency to match the grid. Undersea cables carry the electricity to shore substations. Because ocean environments are so harsh, all components have to be resistant to things like saltwater corrosion, biofouling, and the fatigue caused by constant cyclic loading. Compared to older forms of generation, wave energy offers some advantages and differences that are worth highlighting. Unlike wind or solar, wave energy is highly predictable several days in advance, mostly because of stable weather patterns over the Atlantic. It also has a higher energy density, so a small device can capture significant power relative to its size. However, the mechanical stress in the corrosive environment out at sea are more challenging than what onshore wind turbines or photovoltaic panels typically face. Where older technologies rely on established supply chains and decades of refinement, wave energy is still in the stage of learning from prototypes and pilot farms. Portugal's experience with the Aguçadoura wave farm back in 2008 is a useful case study. This farm consisted of 3 Pelamis devices, each one rated at 750 kilowatts, giving a total capacity of 2.25 megawatts. The attenuators were installed about 5 kilometers off the coast near Póvoa de Varzim. Even though the project faced some technical and financial setbacks, it showed that grid-connected wave energy could operate at utility scale. The data collected from this project still informs newer designs in Europe today, showing the importance of early deployment even when commercial success isn't immediate. Modern Portuguese research is focusing on durability and cost reduction. Devices are now being redesigned with composite materials to help resist corrosion and also reduce weight. Control systems are being developed to tune these devices to different sea states, so they can maximize energy capture without overstressing any components. Engineers are also looking into modular power takeoff units that can be swapped out at sea, which reduces downtime. These advances illustrate how wave energy is following the same innovation path that wind turbines once took, moving from those early experimental machines toward more standardized and reliable equipment. The near-term outlook for Portugal includes demonstration projects that are rated between 5 and 20 megawatts. By 2026, it's expected that at least one new multi-device farm will be operational off the Portuguese coast and connected directly into the national grid. These farms will serve as test beds for things like industrial-scale maintenance, deployment by specialized vessels, and integration with other marine activities such as offshore wind. They'll also provide valuable data for assessing economic viability in markets that reward predictable renewable generation. In the medium term, developments could involve hybrid offshore energy parks that combine wave converters with floating wind turbines. Both of these technologies share mooring and cabling infrastructure, which helps to reduce costs. And by combining the two, power output is balanced, since wind and waves usually peak under slightly different conditions. Portugal's position along the Atlantic makes it a strong candidate for these kinds of hybrid installations. This integration requires new grid management techniques to handle two variable inputs at the same time, but advances in smart grid systems are definitely making this feasible. Looking further ahead, wave energy could play a role in stabilizing continental grids by providing distributed coastal generation. The European Union's energy strategy includes diversification of renewable sources, aiming to reduce reliance on imported fuels. Portugal's wave resource could be exported through interconnections to Spain and France. Coupling wave energy with green hydrogen production offshore is a promising path. Surplus electricity from wave farms can run electrolyzers that are located on floating platforms, producing hydrogen that can then be piped or shipped to shore. This model avoids some of the challenges that come with direct grid integration. But despite all this potential, wave energy does face some clear limitations and challenges. The capital cost per kilowatt is still higher than wind or solar, mostly because of the durability requirements and the smaller production volumes. Devices have to survive extreme storms without structural failure, which means you need both robust materials and intelligent shutdown procedures. Maintenance at sea is expensive, so any technology has to minimize the need for heavy lift vessels. Environmental considerations also come into play, since these devices can affect sediment transport, marine life behavior, and even fishing routes. Each deployment needs to undergo rigorous environmental impact assessments. Comparisons with tidal energy highlight both similarities and differences. Tidal systems, such as underwater turbines, exploit predictable gravitational cycles, whereas wave systems respond to variable weather-driven forces. Tidal flows are site-specific and limited to narrow straits or estuaries, while wave energy can be harvested across broad coastlines. However, tidal turbines benefit from smoother flow conditions, leading to more predictable mechanical loads. Wave devices must therefore be more adaptive, capable of handling a wide range of frequencies and amplitudes. This adaptability makes them more complex, but also potentially more versatile. An important technical area is control strategy. Devices can be equipped with sensors and algorithms that adjust resistance or damping in real time. By tuning to the frequency of incoming waves, they maximize energy absorption. This is similar to resonance in mechanical systems, where energy transfer is highest when frequencies match. Active control requires reliable power electronics and robust feedback systems. Without proper control, devices risk either underperforming in mild seas or breaking under extreme forces. Portuguese engineers are leading experiments in this area, aiming to refine algorithms that balance efficiency with survivability. International collaboration plays a role in Portugal's development of wave energy. Projects are often co-funded by European Union research grants, with test centers located in Portugal, providing conditions for companies across Europe to trial their machines. This exchange accelerates learning by comparing different designs under similar sea states. It also spreads risk, since no single company has yet proven a fully commercial model. The open testbed approach ensures that knowledge gained benefits the broader industry. even if individual projects do not reach commercialization. The economics of wave energy are influenced by learning curves similar to those seen in solar and wind. Early devices are costly due to custom fabrication and small batch sizes. As more units are produced, standardization and mass manufacturing drive costs down. Balance of plant, such as mooring and cabling, also benefits from repetition and experience. Analysts predict that if Portugal and other nations can sustain steady deployment of tens of megawatts per year, costs could halve within a decade. Achieving this requires stable policy frameworks and investment incentives. In conclusion, Portugal's pursuit of wave energy is not simply about adding another renewable source, but about advancing a technology with unique physical principles and practical challenges. The mechanisms, from point absorbers to oscillating water columns, demonstrate how engineers convert the restless motion of the Atlantic into electricity. Each prototype, pilot project, and test farm contributes to a growing body of technical knowledge. With near-term farms expected by 2026, medium-term hybrid parks combining wind and wave, and long-term visions of hydrogen integration, wave energy is progressing steadily. Thank you very much for watching. Please like and subscribe.